Good afternoon, everyone. I hope that you had a wonderful weekend and that everybody's doing great today. We're kind of heading into the home stretch here, 3 more weeks of classes. We're looking today at 31.15, which is just a continuation of all of the area problems we've been working on. In the first part, when we were learning about area, we learned how you could determine the area from one value of x to another value of x as long as the function was positive and continuous everywhere in an interval. Then what we looked at yesterday was a little extension of that where you had to maybe do a little bit of work to find out some intersection points between a function and the x-axis. Today we're going to go a little bit further. So you can find this lesson on page 12 of the current lesson handout. By the way, in integral calculus, which is what we're working on now with antiderivatives, finding areas associated with functions is one of the main applications in calculus. It has numerous applications in the physical sciences as well as economics areas. However, due to time constraints, we're not going to be looking at any of those applications. We're only concerning ourselves with the mathematics involved. Example 7 asks us to find the area between two curves. One of the curves is y equals 1/2 x plus 4, and the other curve is a quadratic function, y equals x squared minus 4x plus 6. And if we were to take a look at these two functions, this is what they look like. And because they intersect and enclose an area, you're not told in this problem, example number 7, the lower boundary of the area and the upper boundary of the area. So one of the things we're going to have to do to begin with is we're going to have to find out what the x-coordinate is of those 2 points of intersection, because we're going to be needing those numbers. You can probably see that they are 1/2 and 4, based on the picture of the graph that you're looking at, but we have to be able to find them algebraically. So when you're solving for points of intersection between two functions, you take the two functions and you set them equal to each other. I would probably want to multiply both sides of this equation we've created by 2. I would just prefer not to work with fractions unless I had to. Leaving us with x squared plus 8 equals 2x squared minus 8x plus 12. Of course, it's quadratic, so we solve all quadratic equations by first zeroing the equation. We can factor this into 2x minus 1, I believe, and x minus 4. I'll just pause and FOIL that out in my head and see if I get the result, and I do, which means that we have two solutions for x equals 1/2 and x equals 4. So now we know the points of intersection of those two curves. Going back to my graph, I know that the intersection point on the left has an x-coordinate of 1/2, and I know the intersection point on the right has an x-coordinate of 4. So how are we going to find the enclosed area? Don't forget, this is the enclosed area. What we can do is use what we learned 2 lessons ago to determine the area between the x-axis and the red function, which I'm going to call from now on the upper function. And that's going to be found by anti-differentiating that function 0.5x plus 4 and evaluating it from 1/2 to 4. We can also determine the area below the quadratic function, which is this shaded region, and that area would be found by anti-differentiating x squared minus 4x plus 6 from 1/2 to 4. And then if we subtract those two areas, that's going to give us the area that we want to find. So how are we going to find each of those two areas? Well, we learned 2 lessons ago that those areas can be found by anti-differentiating the function from a to b. So let me write out what it is we're going to have to do. We are going to have to find the area from 1/2 to 4 underneath 1/2 x plus 4, and that can be calculated by taking the integral from 1/2 to 4 of 1/2 x plus 4 dx. We are also going to have to calculate the area below x squared minus 4x plus 6 from 1/2 to 4. And that can be found by evaluating the integral from 1/2 to 4 of x squared minus 4x plus 6. And then we are going to have to subtract those two areas. Now I want you to make a note to yourself that when you evaluate the first integral, which is the first area, you are going to have to evaluate the antiderivative at 4 minus the antiderivative at 1/2. So what we are going to have eventually for this integral or area is we are going to have an antiderivative minus an antiderivative, and then minus for this integral or antiderivative or area, whatever you'd like to call it, we are also going to have an antiderivative minus an antiderivative. And that can be quite confusing. So if I were you, for following along with this example to begin with, I wouldn't try to do it all at once. We're going to do it in stages. We're going to calculate the area for the first integral, and then we'll calculate the area for the second. Then we'll worry about subtracting them. At the end of all this, I will show you a different strategy that I'm going to advise that you use. But for the first example, we're going to stick with this strategy. So I need to antidifferentiate 1/2 x plus 4. Well, the antiderivative of 1/2 x would be 1/4 x squared, plus the antiderivative of 4 is 4x. And we are going to have to evaluate that from 1/2 to 4. We are also going to have the antiderivative of x squared minus 4x plus 6. That will be 1/3 x cubed minus 2x squared plus 6x. And we are going to need to evaluate that from 1/2 to 4. For my first area, I'm going to have 1/4 times 4 squared plus 4 times 4 minus 1/4 times 1/2 squared plus 4 times 1/2. Remember, we want to calculate these in stages. There's no way you're going to be putting all of this into your calculator at once. Now be careful here because we have to subtract everything else. So we do need a large set of brackets there. We are going to have 1/3 multiplied by 4 cubed minus 2 multiplied by 4 squared plus 6 multiplied by 4. Then we have to subtract 1/3 multiplied by 1/2 cubed minus 2 multiplied by 1/2 squared plus 6 multiplied by 1/2. All right, I edited out a lot of my calculator work, but when you calculate this, it's 20. When you calculate this, it's 33/16. This piece works out to 40/3, and this piece works out to 61/24. And as you can well imagine, there's lots of room for error buried in amongst all of these numbers. So now what I'm going to do is calculate what 20 minus 33/16 is, and I'm going to calculate what 40/3 minus 61/24 is. I get 287/16, and then over here I have minus 259/24. Let's not forget what these numbers are. 287/16 is the area below the upper function from 1/2 to 4. It's that shaded area. On the other hand, this shaded area, which is the area below the lower function from 1/2 to 4, is 259/24. And we've already established that you have to subtract those two areas in order to get the answer. So we're almost done. We need to take 287/16 and subtract the 259/24. And we get 7.1458 with a bunch of 3's, which happens to work out to, in fractional form, 343/48. Now that is an awful lot of work because, again, each of these two areas are found by evaluating each of two separate integrals. So you have to evaluate the integral on the left and you have to evaluate the integral on the right. But I'm going to show you that there is an alternative approach that we can use here. And because we have sacrificed some material in this course, one of the lessons that I've kicked over the boards has to do with properties of integrals. And it turns out that when you have integrals that you are adding or subtracting that have the same upper and lower boundaries, they're both from 1/2 to 4. This is 1/2 x plus 4. By the way, 1/2 x plus 4 is called the integrand. It's what you're anti-differentiating. The integrand of the second one is x squared minus 4x plus 6. It turns out that as long as you have the same upper and lower boundaries, 1/2 to 4 in this example, that you can evaluate one integral over that same domain, and the integrand will be what you get when you combine the integrals. In this case, we're going to be subtracting them. And you can do this whenever you are adding or subtracting integrals. But again, they have to be over the same domain. Before we go any further, you have to accept that this is true, but before we go any further, you should simplify that integrand. The whole point of doing this is you don't have to do two antiderivatives. You don't have to do this antiderivative and this antiderivative. You only have to do one antiderivative. So make that integrand, the thing you're going to anti-differentiate, as simple as possible. This goes from 1/2 to 4. I'm going to have a negative x squared. I have 1/2 x minus negative 4x, which is 9/2 x. Then I have 4 minus 6, which is negative 2. There's another property of integrals that sometimes makes your job a little bit easier. And in this case, it's a preference. You may like to do it or not. I'm going to do it. You are allowed to factor out any factors you want out of an integrand. So I'm factoring out a negative 1 because I don't want to have to grapple with a negative x squared, especially given that in a minute, that negative x squared would become negative x cubed times a third. I don't want to have to deal with that negative. I'm going to leave that negative outside. That makes this minus 9/2 x, and then that makes it plus 2. And now if you look at what we're doing, we're evaluating one antiderivative. We need to figure out what the antiderivative of x squared minus 9/2 x plus 2 is, and it will be 1/3 x cubed minus 9/4 x squared plus 2x from 1/2 to 4. And you're only going to have to subtract once here. If you go back and look at what we did, you had to subtract once to find one area, then you had to subtract another time to find another area, then you had to subtract the two areas. Because we've subtracted the two functions to begin with, we don't have to worry about two pairs of subtractions later on. So we will have negative 1, and then we are going to have 1/3 times 4 cubed minus 9 quarters times 4 squared plus 2 times 4 minus the exact same thing, but instead of using 4, using 1/2. 1/3 times 1/2 cubed minus 9 quarters times 1/2 squared plus 2 times 1/2. I think you would agree there's a lot less work here. The only problem is this is relying on a rule, and we'll summarize the rule at the end of this. So this isn't going to be something that makes sense to you in terms of subtracting areas, because we're not subtracting areas, we're subtracting functions and finding one area. Anyway, let's figure out what this is equal to. We still have the -1. I'm going to figure out what this is, minus, we will figure out what this part is. Four cubed is 64, minus 9 divided by 4 multiplied by 4 squared, which is 16, plus 8. This gives me -20/3. If I calculate the other piece, I have 1/3 multiplied by 1/8. 2 cubed is 8. Minus 9 divided by 4 times 1/4. When I square a half, I get a quarter. Plus 2 times a half is 1. Which gives me (23/48). I had -20/3 here, minus 23/48. So I'm going to take -20 divided by 3. I'm going to subtract my 23/48, which gives me this number. I'm going to multiply it by -1, which gives me 7.1458333. Of course, I hope you recognize it because that's the exact same answer we got before. The answer is 343/48. All right, so what we learned from the first example is that whenever you have one function, which I'm going to call f sub upper, and a second function, which I'm going to call f sub lower, if you want to determine the area between those functions from x equals a to x equals b, we have discovered or learned that that enclosed area can be found by either finding the area associated with the upper and subtracting from that area the area associated with the lower by evaluating two separate integrals, or what we can do is subtract the integrands first. So this is the difference of the integrands. It's always going to be the upper function minus the lower function. And what I'm recommending is you do this. The very first method, where you find each area separately and subtract them, makes sense, because when you look at it visually, you have to take one area, which is a larger area, and subtract a lower area, which is a smaller area. That makes sense. But it's an awful lot of work because each of those two integrals in the first method involve a subtraction of two antiderivatives. And it also involves two different antiderivatives. The second method, which is what I'm going to use from here on in, involves one antiderivative because you're going to get one integrand. All right, example 8, find the area between these two functions, y equals negative 3x plus 1 and y equals x squared minus 5x minus 7. Well, we can go back and use some knowledge that we've gained from Math 20-1, and that's that this quadratic function, since the leading coefficient is positive, is going to be a parabola that opens upward. And going back to grade 10, since that linear function has a leading coefficient that's negative, the slope is negative, which means it will be a line sloping down and to the right. And we can use a little bit of kind of common sense here. If you're asked to find the area between the functions and you're not told from where to where, we assume that there are going to be two intersection points. And what we would like to know are the two values of x for those intersection points. So we're going to solve this equation. Negative 3x plus 1 equals x squared minus 5x minus 7. Zeroing this equation gives x squared minus 2x minus 8 equals 0, which factors into x minus 4, x plus 2. That tells us x equals negative 2 and x equals 4 are solutions. That means that our assumption was right. There are, in fact, two places where these curves intersect. The first is where x equals negative 2, and the next is where x equals 4, which means the area that we're after will be the integral from negative 2 to 4 of the upper minus the lower functions. So when we look at the enclosed area, this is the upper function. Where that area is shaded in, the straight line forms the top of the area. This, on the other hand, is the lower function. So our integrand will be negative 3x plus 1 minus x squared minus 5x minus 7. All right, here we go. Remember, of course, you want to simplify that integrand first. You don't want to anti-differentiate 5 terms when instead you could anti-differentiate 3 terms. I'm going to have a negative x squared. I will also have a negative 3x minus negative 5x is 2x. Then I'm going to have 1 minus negative 7, which is plus 8. Now I can anti-differentiate. So I'm going to have negative 1/3 x cubed plus x squared plus 8x evaluated from negative 2 to 4. You'll notice this time I didn't factor the negative 1 out. You certainly could factor the negative 1 out, but it's a preference. At this point, I suppose you could check your work by differentiating your answer there and seeing if you get negative x squared plus 2x plus 8, and you do. So our area will be negative 1/3 multiplied by 4 cubed plus 4 squared plus 8 times 4. Then we're going to have minus the same expression evaluated at negative 2. That's negative 1/3 multiplied by negative 2 cubed plus negative 2 squared plus 8 times negative 2. And now we can calculate each of these. Negative 1/3 multiplied by 64, 4 cubed is 64, plus 4 squared is 16, plus 32. The first part of our antiderivative calculation is 80/3. The second part, we have -1 divided by 3 multiplied by -8, because -2 cubed is -8, plus 4, because -2 squared is +4, minus 16. Gives us -28/3. So we get 80/3 minus -28/3. Let's see, that's 108/3. I think that's 36, but I'd better double check here. So the area here is 36 square units. Now, is there a way to check this on your calculator? Well, yeah, there is. I wouldn't recommend going back to the beginning and trying to decipher it in terms of areas of each function. What I would do is go to the integral that you built based on the two functions. And you have to have some level of confidence here that says you subtracted the two functions properly and you correctly determined the x-coordinates of the 2 points of intersection. And if you did your work correctly, when you graph the integrand, -x² plus 2x plus 8, you're going to discover a couple of things. One of them is the graph of the integrand will have x-intercepts exactly equal to your upper and lower boundaries for the integral. The other thing you should discover is that the graph lies entirely above the x-axis between those 2 points. You can see that it does cross at -2 and 4, and it is above. So now we can go to our calculate menu, choose the integral from -2 to 4, and we got 36, which is what we got when we did it on paper. So there is a way for you to check your work. Now, one last example, and this example really may not seem like anything new, but I need to talk about it. When we take a look at this function, this parabola is a parabola that opens up, and it says, what's the area between the x-axis and the function? Well, if you have a parabola that opens up, and it says between the x-axis and the function, and it doesn't tell you from where to where, the assumption is that it opens up and it has 2 x-intercepts. And that means that you're trying to find this area. Well, let's find those x-intercepts first. This is the x-axis. To find x-intercepts, you let y equal 0. Pretty simple quadratic expression to factor. It factors into x minus 2, x plus 1. Which means that x-intercepts occur at -1 and 2. So this is -1, and this is 2. Now there's a problem here, and it's the only reason why I'm giving this final example. What some of you might do is say, I'm going to anti-differentiate from -1 to 2, x² minus x minus 2. But that is going to be wrong, because this rule that we have for a single function only works if the function is above the x-axis. So there are 2 things you can do to correct this. One of the things you can do, and if you've taken physics with me, you understand this a little bit better than if you haven't, is recognize that since that area is below the x-axis, that area is negative. Which means that this integral that I wrote needs to be multiplied by -1 in order to give you the proper area. That's one of the options. And we can evaluate this, and we will in a minute. The other option, though, is to use what we learned today and call this the lower function and call the x-axis the upper function. In the region whose area is bound by these lines and curves, this is the top of the area, and that's the x-axis. So the lower function is x squared minus x minus 2. The upper function is 0. The equation of the x-axis is y equals 0, which means if you use the rules that we learned today, the area will be the integral from -1 to 2 of the upper, which is 0, minus the lower, which is x squared minus x minus 2. What we're going to get here is the integral from -1 to 2 of negative x squared plus x plus 2. But that's the same as the integral I have in the box. If I multiply that -1 outside of the integral here I'm going to get the integral I have at the bottom. Or conversely, if I factor the negative out of the integral I have here, I'm going to get the result of what I have in the box. If you don't do either of these, you're going to get a negative answer, and that would be wrong for area. So let's finish this problem. I need to anti-differentiate this. I'm going to have -1/3 x cubed plus 1/2 x squared plus 2x evaluated from -1 to 2. Which is going to give us -1/3 times 2 cubed plus 1/2 times 2 squared plus 2 times 2 minus -1/3 times -1 cubed plus 1/2 times -1 squared plus 2 times -1. All right, I didn't feel like doing a whole bunch of talking while I typed this into my calculator. The first part of your area calculation, the antiderivative at 2, works out to be 10/3. The second part, the antiderivative at -1, works out to -7/6. When you subtract them, you get 9/2, or 4.5 square units. And I have checked that on my calculator previous to this lesson, so I know that that's correct. We're done with area now. There are a number of questions I've outlined in your handout on page 461, 1C, D, E, and G, or what I would call basic questions dealing with upper functions and lower functions. And then the rest of the questions are either intermediate or challenge questions. I should point out to you, because I don't think I have, that this idea for the area between two functions being found this way always works no matter where the functions are. Even if both functions are below the x-axis or partly above and partly below, this will always work. When you're looking at areas between two functions, it will always work. So anyway, there are some questions you can work on. I hope that you have success with these problems, and I will talk to you later. Have a great day.